Hey guys, it's time for another little video. So here we go. The goal of this video will be to give kind of an overall about heat and heat capacities and enthalpies, and then I'm gonna go through problem set 33 and 34, kind of like I did with problem set 32, and talk you through what I'm thinking as I'm solving these problems. A lot of you have expressed that the hardest thing about this is not the equations themselves, but knowing which equation to use. And that's just how it's going to be. So let's talk about the different equations that we're dealing with, and then I'll actually go through problem set 33 and talk about it specifically. So the main difficulty here is, or I guess the main point of these problems is that we are trying to calculate heat. Or if we're not trying to calculate heat, then we're using heat in order to calculate other things. And all of this is based off of the first law of thermodynamics, which is that the total change in energy, the universe has to equal zero. Energy can't be created, nor can it be destroyed. It can only be transferred either between two different things or two different types of energy. So most of the problems that we are doing have to do with energy being transferred from one thing to a different thing. And that's just done as heat. And so we need ways to quantify heat and to calculate heat based off of variables that we know how to measure. So the big variable that we know how to measure is temperature. So we want a relationship between heat and temperature. Well, that relationship is going to be different for different materials, because some different materials change temperature different amounts in the same amount of heat. So the good example is like the pavement versus grass when you walk outside, right? They've both been in the sun for the same amount of time. They've been absorbing the same amount of heat, and yet the temperature between them is different. The temperature of the grass will be cooler than the temperature of the pavement. Well, why is that? The reason is that water has a higher capacity to absorb heat than pavement does. The result is, for the same amount of heat, water has a higher capacity to absorb it without changing temperature, so the water will not increase in temperature as much as the pavement does. So what am I describing here? I'm describing heat capacity. Heat capacity is the capacity for a material to absorb heat before changing temperature. In other words, heat capacity, which is C values, that's a heat capacity, that relates the amount of heat absorbed by something and the temperature that it changes. Okay? And so, I've talked about different ways to calculate Q. One type of way to calculate Q is when you're dealing with only a temperature change. If we're dealing with only a temperature change, then we're going to use a C value. Okay. Technically, there's three different types of C values. That's kind of this first question here. What's the difference between heat capacity, molar heat capacity, and specific heat capacity? I've used these terms interchangeably as I've taught the class, but maybe I can differentiate it now for you guys. So let's first talk about heat capacity. Heat capacity is usually a big C value. Let me do this because I'm going to now break this down. Heat capacity is a big C value, and it's usually in units of, I'm going to write the units in a different color. It's usually in units of like kilojoules, per mole. Essentially, sorry, not per mole, kilojoules per degree Celsius. There we go. Essentially, how many kilojoules does it take to raise the temperature of something 1 degree Celsius? Okay, again, relating heat to temperature. So, if I can take this specific heat, this heat capacity C, and multiply it by the change in temperature that my object undergoes, that's going to give me my overall Q. So remember that Q is always in units of joules or kilojoules. there's my gray, is always in units of joules or kilojoules. Okay, so if I take this kilojoules per degree Celsius C and multiply it by a change in temperature, which is degrees Celsius, the degrees Celsius cancel, and I'm left with Q, which is just kilojoules. In other words, if I want to change the temperature of something a certain amount, I can take that change in temperature, multiply it by the heat capacity, and that gives me the heat required to change the temperature that much. Okay, so if we're changing temperature, that's one of the types of equations that we can use. Now that'll be for a specific object. So that could be for a brick, or it could be for a table. More often we use that when we're talking about calorimeters. So this is for an object. But what if we don't have an object? What if we just have like a substance? For example, water or pavement, right? We could have a certain amount of this substance, and so we want to get the amount of this substance into our equation so that we can decide, are we heating up 1 liter of water or a milliliter of water, right? We want to decide that. And so maybe I could label this. This is for an object, and this is heat capacity. All right, well, if I'm dealing with a substance that has different amounts of that substance, I'm not going to use a heat capacity. Technically, I'm going to use a specific heat capacity. So, while a heat capacity tells you how much energy it takes to raise the temperature of my object 1 degree, a specific heat capacity tells me how much energy it takes to raise 1 gram of that substance 1 degree Celsius. So then it makes sense that if I'm trying to calculate the total heat, then I'm going to have to multiply this heat capacity by the mass of stuff that I want and the change in temperature that stuff is undergoing, because the mass will be grams and the change in temperature will be degrees Celsius. And you can see the grams cancel and the degrees Celsius cancel, and that just gives me joules. Okay, so that's the Q equals mc delta T. That's the one that you're used to, but that's used if you're just talking about a substance and you have a certain amount of that substance, and that amount of that substance is changing temperature. You're going to use a specific heat capacity, and the unique thing about specific heat capacity is it has grams in the bottom. And that leads us to the other one, which is a molar heat capacity. Okay, and a molar heat capacity is just like a specific heat. I guess I could put, an S there for specific heat capacity. A molar heat capacity is just like a specific heat capacity, except that instead of per gram, it's on a per mole basis. So it's just per mole degrees Celsius. So in this case, I'd have to multiply by moles. I have to multiply by degrees Celsius. And that's going to give me my total heat. Okay, so I really think of these two equations as being pretty much exactly the same. Right, if I have a heat capacity with moles in the bottom, I'm not going to multiply by grams, I'm going to multiply by moles. So I'll just use the term MCAT all the time. Now, this equation and this equation are also very similar. It's just I'm dealing with an object that has a set mass. And so because it has a set mass, I don't need to specify the mass. I could essentially multiply the heat capacity, or the specific heat capacity and the mass together, and that gives me a big C, right? And so again, this is pretty much the exact same equation as this one on top, except that I don't have a mass there because I know the mass of my object. It's not going to change. So again, if we're trying to calculate the Q, and the only thing that's happening is a temperature change, maybe I should clarify what I mean by that. When we say the only thing happening is a temperature change, I mean that your stuff is exactly the same before as it is after. Okay, it's just you heated it up or cooled it down. Okay, that's all that's happening, is that the temperature is changing. And we could differentiate them by specific heat capacity, molar heat capacity, and heat capacity, which is for an object. but I don't usually differentiate them like that because I think that conceptually they're all exactly the same. It's literally just the units that are changing. But you will have to know when, specifically with calorimetry, when you need to just use the heat capacity. You'll have to be familiar with that. So this is how we calculate heat for a change in temperature. All right, the other situation is if, so I said a change in temperature, you have the same object before and after, it's just that the temperature is different. Well, what if that's not what's happening? What if we are doing more than just changing the temperature? Well, what situations have we talked about in our class? We've talked about a phase change, and we have talked about a reaction. Okay, for phase changes and reactions, we don't use a C value. A C value, again, relates heat to a change in temperature. For a phase change or reaction, we're going to use an enthalpy value, a delta H value. Okay, a delta H value, we'll talk about this later, but delta H is just heat. Okay, delta H is just heat. Okay. Sometimes you'll see it written, I'll write it here, that Q equals delta H. Now, when is this true? This is true when pressure is constant, okay, but for our class, pressure is always constant, and so for our class, enthalpy and heat could be synonyms. Okay, does that mean that mathematically, if delta H is 5, Q is 5? It could, but often, and what you'll see right here, is that it doesn't because the units on delta H and Q are different. So maybe a little analogy. Well, actually, let me explain the units real quick. Delta H is usually in units of kilojoules per mole or something like that, a heat per amount, versus Q, which is usually just kilojoules, which is just heat, or energy, I should say. So delta H is energy per amount, and Q is just energy. So a little example. If you go to the store and you buy a bunch of boxes of graham crackers, which are each $2 a box, and I ask you, oh, how much money did you spend at the store? You could say, oh, I spent $2 a box. But is that actually how much money you spent at the store? No, because we need to know how many boxes you purchased in order to know how much money you actually spent in real life. So the cost of your thing was $2 a box, but that's different than how much you actually spent, because again, we don't know how many boxes you purchased. Now, is this $2 a box? Is that in money? Is that money? Yes. Let's say you bought 5 boxes. So overall you spent $10. Okay, so is this money, $2 a box? Yes. Is this money, $10? Yes. But is $2 equal to $10? No, because I need to multiply by the number of boxes that I purchased. Okay, so enthalpy is heat. Q is heat. Just like $2 a box is money and $10 is money. But enthalpy is usually provided in a per amount basis. Just like when you go to buy a box and you go to the store and you see graham crackers, it's not given, it doesn't say the amount that you're going to spend at the store. No, it says the amount for one box. Okay, so enthalpy is heat, Q is heat, but enthalpy is not necessarily the total heat that goes on in your process, because again, it's usually given in a per mole basis or a per gram basis. So if I want to know how much heat is actually involved in my process, we end up with the total heat is equal to the delta H times the number of moles that go through that process. So again, delta H is kilojoules per mole. So if I want to get kilojoules in my heat, I need to multiply by moles. Sorry if I overdid that, but it's definitely a point of confusion for people because we start saying Q and delta H are the same thing. Well, they are. Just like the money, the price of a box and the total you spend at the store are both money, okay? But that doesn't mean that they're equal to each other. numerically. Okay. Cool. So for some process, so here we're changing temperature, here we're not changing temperature. So for every process, there is a delta H value for that process. So if I am burning something, then that process has a delta H, or an enthalpy, of combustion, because we're burning it. If I just have some reaction, that reaction has a change in enthalpy, or a delta H of reaction. If I'm vaporizing something, then there's a delta H of vaporization. Okay, so delta H is just how much heat is associated with that process. Okay? So I just need to know what is my process, and then I can get my delta H for that process, and then multiply by however much stuff I have going through that process to figure out the total heat. Sometimes you will also see Q equals M delta H. Okay, and all that means is that my enthalpy was provided or found in kilojoules per gram. So then if it's kilojoules per gram, should I multiply by moles? No, I should multiply by grams, and that will give me kilojoules. So again, similar to how we saw on the change in temperature stuff, the MCAT equations, these two equations in my head are exactly the same. It's just you need to check your units as you're doing the equation. So, so these are the two types of equations, or you could say the 5 equations that we will use to calculate heat. And as much as you might disagree with me, these are the only equations that we have ever used to calculate heat. Everything we've done has fallen into one of these equations. And I would argue that really there are 1, 2, 3 equations, and that these two are just duplicates of the ones above. So I wanted to go over all of that right now, because now as I go through this homework, I want to be able to explain my thought process and always relate it back to these equations. Okay?